Okay. All right, so I'll post the answer key to this exam when I get back to my office after class. It'll be in today's folder, and then hopefully I'll get these graded today, and you'll have them tomorrow. So today we're going to do for the rest of our time is we're going to finish up E2, including doing E2s on ring systems. Did I give you a marker and a? Yeah.
So when do we stop learning the material?
When do you stop learning the material? On Wednesday at about 10:15. Because what we'll do on Wednesday is we'll spend the second half of the period kind of going over things.
And then the final exam, is that like kind of like emphasis on stuff we did this week, or is it kind of?
It's going to be completely comprehensive over the entire, from beginning to end. So probably in equal amounts. So there won't be any overemphasis on what we do in the next 2 days, 2.5 days.
And then for next, like organic 2, is that comprehensive what we learned here and in the second?
Yes. So that the final exam for the next, at the end of the next session, organic 2 will be comprehensive over the entire 2 sessions, and it'll be the ACS final. It'll be the ACS exam. So, but let's get through this final exam first, and then.
ACS counted as like final.
Yeah. So when we get to that point, I'll talk about how I grade it and everything. But it is a final exam first, and then with a small sample number, I do use it for assessment. But then again, I'm assessing mostly non-John Carroll students. During the semester, I'm assessing what students are doing in our program. So, but we'll still take that exam. You'll still take that exam. Now for Thursday, you will see that I released some multiple choice questions that I've written for the first semester. Now there's some free radical halogenation reactions on there that aren't going to be part of this, but there is some stereochemistry, there's some E1, E2, there might be some stuff over that might be alkene reactions that we'll get to tomorrow and half the period on Wednesday. So if you want to start reviewing, that would be a good place to review with those multiple choice questions. There are also ACS study guides that are listed that have other multiple choice questions, but those are on reserve over in the library. I don't know how you get access to them if you don't have a John Carroll ID, but they probably would let you do that.
Is the exam going to be a final exam for like 2 hours?
The final exam you have 2 hours for it. You would have 2 hours for it under normal circumstances. So that means Thursday is just dedicated to the final.
I hope you had naming alkynes in that folder. Are we going to continue the
We're going to name alkynes when we get to alkynes, which is in the next class. Because I'm not going to make it completely through the reactions of alkenes. I'm not going to push it.
So there won't be naming.
There would only be naming of alkanes, alkyl halides, and alkenes. And there might be some easy naming. Right? I mean, this was not that long ago. It's not like this is December and you started in September. So hopefully with the compressed time frame, stuff hasn't shot out of your head yet. So we're going to make it as far as we make it, and then we pick up there next semester for those of you who continue on. Okay, so that's in the multiple choice are in that folder so that you could, review those, use those as review. You could also use any of the chapter problems in Top Hat, the end of the chapter problems as review as well. Okay, so finishing up E2. Couple of issues with the E2 mechanisms. First of all, we know that for the E2 mechanisms that these were our two bases, tertiary butoxide and NH2 minus. Those are our two bases. When you see those bases, they only do E2. That's it. So that's going to be the telltale sign that something is doing E2. And then you know what the difference is, right? NH2, what kind of product does it give? Right, it gives the most substituted product, the Zaitsev product, the most substituted alkene. And the tertiary butoxide, it removes the least sterically hindered hydrogen, beta hydrogen. Now you might say, okay, the book talked about the Hofmann product, which is oftentimes the product that is not the Zaitsev product. The Hofmann product is the one that's least substituted. The reason why I've said that the tertiary butoxide removes the least hindered beta hydrogen is because if you use that as your definition, it'll work with every problem I give you. Because there are problems where it's not necessarily you're forming the least substituted product. And we'll see that today. We'll see an example of that today. Okay, so we need those two problems. Now in the Top Hat textbook, they talked about solvent effects. And what I will say about solvent effects is that these two bases, since they're strong bases, these strong bases are not going to be used in water. Why wouldn't they be used in water? Because actually both of these bases would deprotonate water. And so then they're no longer strong bases to do E2. So we can't do E2 reactions in water. And they're really not used in alcohols either, because the NH2 minus on the periodic table, N minus is a stronger base than O minus. The N minus will rip the hydrogen off of water, and again, you won't end up with an N minus, you'll end up with ammonia and a hydroxide. So neither of these two bases is compatible with water, and neither of them is compatible with alcohols. And that's the most important thing to remember. So you're never going to see an E2 reaction in water or in alcohol. They're going to have to be in a solvent that doesn't have any hydrogens that can be removed. Actually, DMSO would not be compatible with NH2 minus because NH2 minus can deprotonate DMSO. And that's why I use the hydroxylic as opposed to the protic terminology, because that's a perfect example of something that has protons that can be removed. DMSO has a hydrogen that can be removed with NH2 minus, so it really doesn't fit the aprotic nomenclature. Right. So that whole section can just be reduced down to that. Now, when we have a cyclohexane or a cyclopentane ring, and I have my leaving group in a particular stereochemical position, like in a boulder-dashed wedge, there is a question here about what hydrogen is going to be removed in an E2 reaction. So if this is my alpha carbon and I have 2 beta carbons, let me just for the sake of argument add 2 methyl groups to that beta carbon so there's no hydrogen that can be removed. So you can't remove any hydrogens from the top beta carbon. And then I've got a hydrogen here and I've got a hydrogen there. We'll call that HA and HB. So the question then is going to be, given the fact that E2 has to go anti-periplanar, which of those 2 beta hydrogens can be removed? Could HA be removed? Could HB be removed? Both of them? And one of them has to be removed, at least one. So would it be A, B, or both? Okay, that was going to be a rhetorical question, but you can answer it if you'd like.
B.
Why?
It's trans, so the CL and anti-periplanar.
In this case, it is both of those. It is trans and it is anti-periplanar. So let's draw this out. Now, the only way the leaving group and the hydrogen can be removed in an E2 reaction in a cyclohexane ring is if they are in the 1,2 position, relatively speaking, since this is still the alpha carbon and that's still the beta carbon. Any questions? Okay. So there's the alpha carbon and there's the beta carbon. Now, in order for me to put the leaving group and the beta hydrogen anti-periplanar, where do those groups need to go? Axial or equatorial to be anti-periplanar? Both axial? So the chlorine's going to be here and the hydrogen's going to be there. So in order for the base to be able to truly come in and grab this hydrogen and have that pair of electrons move there and have the chlorine leave, the beta hydrogen and the leaving group in a cyclohexane ring must be both in an axial position in order to form that anti-periplanar geometry. Now in this case, if we go back and we remember how to convert from the ring, the flat ring, to the chair, actually HA would be here, and then HB would be below the plane of the ring. So in the molecule that I wrote this way, the chlorine and the hydrogen HB are actually both anti-periplanar. But in the future, what we're going to be interested in is we're only interested in the fact that the leaving group and the hydrogen, the beta hydrogen, are trans. That's going to be the critical part. Because you could say, well, what if you put the chlorine in an equatorial position? It can't undergo E2. If I put the chlorine in an equatorial position, it will not undergo E2 until it does a ring flip. And when it does a ring flip, then the chlorine becomes axial, but the other hydrogen that was trans to it will then become axial as well. So our critical part is that we need to have the beta hydrogen and the leaving group trans. That's the critical part. But the reason for them having to be trans is because that's the only way you're going to get the beta hydrogen and the chlorine to be in an anti-periplanar geometry. And if they aren't, then you have to apply additional energy to do a ring flip. Because remember, for E2, the first issue is that the beta hydrogen has to be antiperiplanar. If it is not going to be removed. And so that double bond will not form there by E2. Is everybody with me on that?
So the axial part it's more the trans versus the axial?
Right. So even if the leaving group isn't axial, I can make it axial by doing a ring flip. So what I'm more concerned about is, because now we're going to do problems that look like this with the ring with the cis and the trans groups. And so I don't have to worry about, well, is that chlorine axial? I'm not going to worry about that. What I'm going to worry about is that chlorine trans to one of those hydrogens, because that's the hydrogen that's going to be removed. So in this case, HB that's the only hydrogen that can be removed by tertiary butoxide or by NH2 minus. Now, when that reaction occurs, we would end up with a double bond there, and we would end up with a hydrogen here. And unless I did something to those two hydrogens to be able to tell whether I removed HA or HB, I'd get the same product. So when people worked out this mechanism, what they did was they were able to put the isotope of hydrogen with a mass of 2, which is called deuterium. There's no D on the periodic table. D stands for hydrogen with a mass of 2. They were able to synthesize the molecule and put the deuterium in either the axial or the equatorial position and do the reaction, and then they could see whether or not the D showed up in the final product. Because if the D showed up in the final product and it was going to be axial, it shouldn't. Or if it didn't show up, then that's why. So people have gone through the mechanism using that isotope to figure out exactly, well, to confirm that it's antiperiplanar. Okay. So that's what we're going to have to look at with these rings, these ring systems. Leaving group, only the beta hydrogens that are trans to the leaving group are going to be able to be removed by the base. However, what about an E1 mechanism? So in other words, if I took that same molecule and said, okay, I've got HA and I've got HB, but now I'm going to do this reaction by E1, which hydrogen, HA or HB, could be removed? We agreed it's both? So if I change that mechanism, that chlorine's going to leave, and if I look at my ring system here, I'm now going to end up with the carbocation and remember, in E1, the beta hydrogen only has to be parallel. It only has to become parallel with one of the two empty lobes. So I could rearrange, rotate this bond so that HA is parallel to the empty lobe, and that also that HB is parallel to the empty. So in this case, either, well, or both hydrogens could be lost. So that means there's no stereochemical restriction for E1. Either hydrogen, cis or trans. So either the cis or the trans beta hydrogen can be lost in an E1 mechanism. So you can lose either one of those. So the stereochemical restriction is only in E2, not in E1. Is everybody with me on that? Let's find out. So here's a reaction. Tell me what the major product is. And so that's why I gave you the little whiteboard with the Sharpie and the eventual paper towel to erase, if these things will erase. Okay. So tell me, write what the major product would be. You need some more things on it. Okay. You want to make sure you put the ethyl group. What do we have? Okay. What did we hit? What did? Well, yeah, but the whole purpose was you don't see somebody else's to. Okay. Do you have two, Alex? Just one. Which one? Okay. I'm gonna kind of write big too. No, it's not like the big cards where I have to actually be able to see it. Okay. So it's really easy for me to come up with answers here. My answers would be, here's my alpha carbon, here's my beta carbon, here's my other beta carbon. So all I have to do is just put the double bond in between all the possible alpha and beta carbons, and I have all my possible answers. Now, one of the things that you need to, well, if you have a double bond, bold and dashed wedges attached to a double bond don't mean anything. Because the way the double bond is here in the ring, all four groups got to be in the plane. So if you write a bold or dashed wedge trying to indicate that it's cis or trans, it doesn't. It just doesn't, it's not appropriate. So here's two possible products that people wrote. And then what's the third possible answer? No reaction is always a possibility. So then if I wanted to do this by multiple choice, I would say, okay, there's A, B, and C, and then D would be A and B together. 50-50. Okay. And I don't have my phone, so we can't do the thing with the cards. But I saw all these different answers. So which one is correct? B? C? So how are we going to know? So what I just did is wrote all the possible answers. Now, can they form? So in other words, one of the approaches to solving this problem would be, okay, let's write all the possible products showing the double bonds between the alpha and the beta hydrogen, or between alpha and beta carbons. Then let's see if any of these can form, because if they can't form, they can't be a possible answer. So what's the criteria of being able to form the product?
The beta hydrogen has to be trans and
And what's more important here is trans. So in this problem, because if I put the leaving group on a dashed line, we would look for beta hydrogens that are going to be cis to it. So trans is going to mean also anti-periplane. So to simplify that, let's go through each beta hydrogen and is it trans to the leaving group? Now you might say, well, wait, where's the top for the top hydrogen? For the top beta hydrogen, where is it? Because I didn't write it in. So where should it go? Where should this hydrogen go? What kind of bond? Bold, dashed, regular? Karen? Bold? How do you know? So in this tetrahedral carbon, I've got two bonds in the plane, a dashed one, so what do I need? I need a bold, and that's where the hydrogen goes. Down here at the lower beta hydrogen, where should it go? Bold, dashed? It should go on a bold wedge as well. Okay. So as you can quickly see, there's a lot of steps that we have to do either in our head or on paper in order to answer this problem. So what I will do is I will write, if I'm going to ask this by multiple choice, I will give you all the possible alkene products, and then you have to figure out, number one, which ones are possible, And then of those ones that are possible, which ones actually form? What's the major product? Okay, and if I don't show you the hydrogen on the ring, you got to be able to put it in.
So this is E2 then?
So that's the other thing. When I see NH2 minus, what's the mechanism? E2, always E2. So we know this is an E2 mechanism. The ethyl group is there. And that's the other thing you got to do is draw, if you're uncertain where the double bond should go, draw the molecule without the leaving group, and then just write a double bond to each of the alpha beta, each of the double bonds to each beta carbon. Okay, so basically I've got my possible reaction or possible products. So let's take the product, the hydrogen that gives you A, here's the hydrogen that gives you product B. Can HA be removed in an E2 reaction? Yes, no. No? Anybody say yes? Anybody not know why? HA has to be what to the chlorine in order for this E2 reaction to occur? HA has to be trans. Is it? No. Can it become trans? Never. Because two groups that are cis are always going to be cis. And in the 1,2 system, the only way to be antiperiplanar is to be trans. If you're cis, you can never become antiperiplanar. You can't twist the molecule around to make that happen. So it's got to be trans. So can HA be removed? No. How about HB? No. So HA and HB cannot be removed. Why? Because the beta hydrogen is not trans to the leaving group. So that leaves me with what? That leaves me with no reaction.
Why did the beta hydrogen and the be equatorial?
They can't be equatorial and trans. Well, in the 1,2 system here, okay, there's the 1,2. The only way to get those in the antiperiplanar geometry is to be in those positions. These equatorial positions, I can never twist the ring I can never twist the ring around to get those two squares antiperiplanar. It's just not going to happen. So that leaves these two guys, which are trans, that leaves only the conformation. Now you might say, well, what about the squares? Sorry, the squares actually are trans too. So if I wanted to make these two squares antiperiplanar, what should I do? Just do a ring flip, and if I did a ring flip, then I would end up with the squares both axial. I guess what I should have said is, can I ever make a circle and a square antiperiplanar? And the answer is no. I can't twist this square down enough to ever make it antiperiplanar. So if it's cis, it's never going to be antiperiplanar. If it's trans and they're both like equatorial, just do a ring flip and they'll both become axial, right? Because when we do a ring flip, what happens? Each of the positions is inverted. Brandon? So that's why I'm more concerned about trans than I am about axial and equatorial at this point. So I can never make HA and chlorine anti-periplanar because they're cis. Let's do another. Now I can realize that from this basic cyclohexane, I can probably write 10 different problems. Because if I change a bold and dashed wedge, what happens? If I change the bold and dashed wedge, then I can completely change the reaction. So let's try this one. And I can do this all day. Okay? What's the major product of that reaction? Okay.
How come we have a hydrogen carbon?
Okay. So why can't I remove the hydrogen that's attached to the same carbon as the chlorine? Because what kind of hydrogen is that? In other words, what kind of carbon is this, alpha or beta? So I can only remove the beta hydrogens. Because if I try and remove the hydrogen from the chlorine, if I move that pair of electrons, I could kick the chlorine off, but then I'm going to end up with like a carbocation or something. So, or even worse, a C minus. So in order for the electrons to flow the way they flow, you've got to remove a beta hydrogen. So the first thing you need to do is identify all the possible beta carbons. And so for this one, maybe the thing is, what are the possible products, and then what's the major product? Okay. 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 I see a leaving group. The leaving group shouldn't be there. Okay. Okay, so looks like you're sort of getting the hang of it. What are our two possible products? Go to each of the beta hydrogens, remove it, and then remove the leaving group. And so it looks like our possible products are A and B, with a C being, what's a C? C is no reaction, and D is A and B formed equally. Okay. So for this one with NH2 minus, what did you, I saw most people had letter B. Why? It's the most substituted, but before we get to that, the first question is, so, which beta hydrogens can I remove? Either one of these will give you product A, right? Well, actually, no, that's not true, is it? A1, A2. Which hydrogen has to be removed to form product A? Hydrogen A2. And then hydrogen B can be removed, right? Because it's trans to the leaving group. So in this case, both A and B are possible products, because they both could be formed. So that's always the first step. What possible products do I have? And then we look at NH2 minus, and what is NH2 minus? Well, let me take a step back. First of all, when I see the NH2, I know it's an E2 mechanism, so I have to care about stereochemistry of the beta hydrogen. Then, can I form product A? Yes. Can I form product B? Yes. I'm using NH2 minus, which says that the major product is going to be the product that is more substituted, which is product B. So B would be formed with NH2 minus. Okay. Okay, how about there's no NH2 minus, and I say let's do this reaction with E1 mechanism. So if I do this reaction with an E1 mechanism, what's going to be the major product? And you could just write the letter if you'd like. Got it. Okay. 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 Seems as if we're all agreed that it would be that if this was an E1 mechanism, product B would be the major product. Because again, it's more substituted. Okay. See how easy it is for me to generate all these different problems? Because now what am I gonna, now what should I ask? Now I should ask tertiary butoxide. So if we do this mechanism with tertiary butoxide, if we do this reaction, what should be the major product? Okay. Okay. Don't know. Okay. All right. So it looks like most people thought that A would be the major product with tertiary butoxide. So again, stepwise, tertiary butoxide, E2. Let me find all my beta hydrogens. Can I remove them? We already been through that. Yes, I can remove both A or B. Tertiary butoxide goes after the hydrogen that is least hindered. So which is that, A or B? A, because hydrogen A is attached to what kind of carbon? Primary, secondary, tertiary. Secondary. HB is attached to what kind of carbon? Tertiary. So by definition, secondary is always least sterically hindered versus tertiary. Okay? Okay? Kind of getting the hang of this? All right, let's throw some twists in. Start with NH2 minus. For this one, write the possible alkenes and then show me with a check mark or major which one the major one would be. So write all the possible, and all the possible alkenes means all the possible alkenes. E1 or E2. So write all the possible alkenes using either E1 or E2. And then once we have those written down, then I can go through and ask you, then I'll change the mechanism of the base, and then you can just write underneath it, you can say major or minor, put a check mark, or you put a check mark or major under each of the major products. So first thing I want you to write all the possible products. Okay. 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 So don't erase your, if you put the structures down, don't erase them. Draw them back. What's the O? Oh, sorry, this is a C. It's an ethyl group. It's an ethyl group. Sorry. It's an ethyl group. Okay, if I was doing this reaction by E1, so there's no stereochemical restriction, I would get these three possible products, A, B, and C. Here's my alpha carbon, here's beta carbon 1, beta carbon 2, there's beta carbon 3. We can't forget about beta carbon 3 that's attached outside the ring. So I got 3 beta carbons and I have 3 different products. So which one is the major product? And in this case, if there's more than one major product, you would write both letters or check mark next to each one of them, whatever you want to do. So for NH2 minus, what's the major product or products? Mm, mm. What? Which one? Okay. But you might want to modify your E2 answer. Okay. 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 What do you have? Okay. Okay. Now this is E2. Which products can I form by E2? Let's go down the line. Can I form A from E2? No. So A is not a possible product, major product here. Can I form product B? No, so product B is not a product. Can I form product C? Yes, I can form product C. Why? Because when you have a CH3 group or a CH2-CH3 group outside the ring, there's free rotation. So I can rotate one of those hydrogens to be antiperiplanar to the chlorine. It's only the hydrogens that are attached to the ring that are stuck in cis or trans. But anything outside the ring can be oriented so that it can become antiperiplanar. So is C a possible product? Yes. So what's the only possible product using NH2 minus in this case? C. Oh, what statement? Okay, so with C I have, here's how it looks with the chlorine. I've got a C with 3 different hydrogens, with the 3 hydrogens on it. So I can rotate any one of these hydrogens to become antiperiplanar to the chlorine. So we have free rotation here to make any of those hydrogens antiperiplanar to the chlorine. So only the hydrogens that are cis or trans are the only ones that I can't. They either they have to be trans in order to react. No? So in terms of the system, in terms of what I would propose is probably the best way to go about this problem, is write all the possible structures that you could get. Now, is my next question going to be, what's the major E1 product? Yes, that's what's going to be. But if you treat this as if it was an E1 reaction and write all the possible products where stereochemistry isn't an issue, then you're going to have them all to choose from. So then in the next step, I would say, well, let's look at the base, and if it's an E2 base, which one of these products can be formed? In this case, only C can be formed, so what's the major product with NH2 minus? It's got to be C, because A and B can't be formed. And as a matter of fact, if I said, let's do this reaction with tertiary butoxide, what would be the major product? It would be C. Why? Because it's the only product that can be formed by an E2 reaction with a strong base. To get to this B, to get to this one? Okay, well, so what kind of carbon is that? Primary, secondary, or tertiary? It's just primary, so actually the tertiary butoxide wouldn't have that much of an issue getting there. which could be another potential problem that I could write. So in this exact problem I gave you, the only possible product for any E2 mechanism is product C. So NH2 minus and tertiary butoxide would give you the same answer. We agreed on that? Then what do I have left? I have an E1 mechanism. So by E1, what's the major product? Or products? A, B, C, any combinations of letters? What's the major product in an E1 mechanism? Okay. 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 Half a K. Yes.
I think it was because I thought that we were only
E1 means I'm going to lose the chlorine to form the carbocation, and then I'm going to lose the beta hydrogen.
so you can just drop it.
Actually, I don't use any bases at all. Because the way I've been treating it is the beta hydrogen kind of falls off. There's no base that comes in and rips the hydrogen off in an E1. It's just we form the carbocation, a beta hydrogen can just fall off. But by saying E1, I mean this goes through a carbocation intermediate. So if it goes through a carbocation intermediate, what's the major product? First of all, if it's E1, is there any stereochemical restriction? No, which is why writing the E1 products first gives you all possible answers. But then E1 always gives what kind of alkene? The most substituted. So of A, B, and C, which one is the most substituted? A and B are the most substituted. Why? Because A has 1, 2, 3, 4 carbon groups attached to it, and B has 1, 2, 3, and 4 attached to it. So they have the same number. Over here, only have 2. So for E1, it would be a combination of A and B. So let me just quickly change this problem too. Let's make them all possible. How would I do that? I would do that by changing the dashed lines on the methyl and ethyl group to being bold wedges. So now hydrogen A, hydrogen B, and over here, if this is A, if this is B, that's C. So forming product A is possible in E1 Let me go back. So here's my A, B, and C. So if I started with E1, A, B, and C are now possible products. Well, they were in the last one. All I did was I just changed the stereochemistry of the ethyl and the methyl group. So if I said, in this problem, E1, what's the major product? What'd you say? A and B? We agreed that it's A and B? Okay. NH2 minus. What's the major product? All right. What do we think? Okay. 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 No. No. Well, yes, okay. I see it, but so in this case, can A, B, and C be removed in an E2 reaction? Yes. I changed it so that that happens. So NH2 will give us the products that are most substituted. Which are those products? A and B. So A and B preferentially. Second to last one, tertiary-butoxide. What's the major product going to be with tertiary-butoxide? Can they all be removed by E2? Yes. What's tertiary-butoxide going to do? Remove the least sterically hindered one. So what product is that going to make? C. We all agree? Okay. I said second to last one, now the last one. The last one would be, let me take away that methyl group. So I am taking away, product C. So I want to do tertiary-butoxide with this new molecule, and the only possibilities are A and B. Which one's going to be the major product? And your choice is A, B, or A and B. Okay. 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 So we can get at both HA or HB. HA is what kind of hydrogen? It's attached to what kind of carbon? Primary, secondary, tertiary? Tertiary. HB is a tertiary hydrogen as well. So if you said A and B, they're both tertiary hydrogens. But is there a difference in the steric hindrance around those two? Yes being A is close to an ethyl group and B is close to the methyl group. And so which one of those two is less sterically hindered? B. So with this tertiary butoxide, B would be the major product. So why did I not say the Hofmann product that's least sterically hindered is formed? Because that doesn't predict the major product in this case, where we have to go primary, secondary, tertiary, then we have to look at the steric hindrance. Okay, so I will put on the web, we finished up chapter, I don't know, 10 today. So then we'll start on chapter 11. We will not make it completely through, but that's what we're going to start on tomorrow.
Thank you.
And we'll see how far we get. If you want to leave you can leave that there if you want.
Thank you. I was confused